Hello everyone, my name is Jade Chapa at Brain Scanology, and in this presentation I will be explaining how the LCPC transform measures the shape of Modic types with unprecedented precision. Our software will allow surgeons and radiologists to make sense of the complex clinical data associated with Modic types. We measure shape in a way that area and volume cannot, which allows for precise machine learning predictions that generalize across datasets. We also measure shape and not signal intensity, so our software also works on low-resolution MRIs from older data archives. Modic changes describe defects in the end plates of the human vertebra that are adjacent to spinal discs. Modic changes are correlated with back pain and resistance to surgical treatment. There are three general categories of modic changes that are defined by their signal intensities in T1 and T2 MRI scans. Though there are up to 6 categories of modic changes, if you consider mixed types such as type 1, 2 combined or type 2, 3 combined, this grading system is crude and needs an upgrade in light of emerging computational image analysis tools. Brain Scanology is eager to prove that its algorithm is above and beyond the rest. Before we begin discussing our results, I would like to go over how it is we achieved our data analysis using the LCPC transform. In order to perform the LCPC transform, in step 1, a mask of the outline of the modic lesion is created. In this case, the modic shape is in blue, and only the roof is outlined. In step 2, we define the baseline of a parallel grid system to be the line that connects the ends of the modic shape, as seen in green. In step 3, a parallel grid spaced every 5 pixels is overlaid onto the outline. This allows us to calculate the distance from the baseline of the parallel grid, which is shown as a dashed line, to the intersections of the parallel grid and the edge of the shape. After that, we can linearize the parallel grid system as seen in step 4. If a grid line does intersect the outline of the object multiple times, the distances on that grid line are summed into one value. And finally, in step 5, we then perform a fast Fourier transform on the data from step 4 to create a frequency plot that is a multi-dimensional representation of the modic shape. Throughout the presentation, we will refer to the fast Fourier transform as FFT. On the x-axis of each graph, this represents the order of frequency bins, and each bar represents the value of magnitude for the corresponding frequency bin. In this presentation, the bin number is the same as the bar number. In the 6th step, we have a frequency plot which can be converted to a scalar value that represents the shape. For example, all bars can be summed into one value. We will begin by exploring a range of phantom modic shapes. Some are shallow lesions, as in the top row, while others are deep lesions, as in the bottom row. The middle column displays the frequency plots showing how the LCPC transform sees these shapes A, B, and C. Multiple indices can be derived from these frequency plots, but a simple one is to sum all bins for each graph. Once we do so, we see the values in the graph on the right. The summed magnitudes reveal a linear increase that correlates with the changes we visually see in the shapes on the left. The taller a lesion is, the larger its summed magnitude. When analyzing the frequency plots of shapes D, E, and F, we see a similar linear increase in the index that sums all bins. Here, we compare two shallowest modic shapes from this first set to show how different their profiles really are. We can derive multiple indices, but on the right, we show the index resulting from summing all bins. In this set of phantom modic lesions on the left, there are 3 different shapes that have varying depths. On the right are mirror images of the lesions on the left. Though the area and volume of an object does not change in its mirror image, we will show that shape is distinct between mirror images. The graphs on the left show how the LCPC transforms sees these shapes. For simplicity, we summed all bins to get an index for each shape, as shown in the bar graph in the middle. As the shape height decreases, so does the index. On the right are sections from the frequency plots on the left, represented by the dotted lines. Now, I'd like to highlight how the hockey stick pattern outlined in green is replaced by a different pattern outlined in red. This difference likely represents the fact that the right end shape 2C, which is the bottom shape, is a near flat line compared to the tails of the upper 2 shapes. This difference in patterns suggests a distinct shape state between 2A and 2B compared to 2C. Zooming into this by truncating the y-axis, we see that the middle bins are indicative of another distinct shape state. This time, it is between the top shape 2A and the bottom 2 shapes 2B and 2C. This difference can be seen in the outlines of green and red, which exhibits opposite concavity patterns. When we compare the mirror images of these shapes, the LCPC transform reveals that the left and right-hand versions of these same shapes are not equal. If you sum bins 13 to 31 in each frequency plot, you'll see that the bars on the right, which are in green, have a larger value for this index than do the bars on the left, which are in red. In our other projects that studied left versus right-handedness, in other words, chirality, we consistently find that the LCPC transform measures left-handed objects distinctly from right-handed objects, even if they are exact mirror images. But what is the big deal about being able to measure the handedness of modic lesions? In other words, what does it matter that we can measure whether the peak of the modic lesion leans towards the anterior end or the posterior end of the vertebra? Well, because in biology, structure is function. Each vertebra has an anterior to posterior axis that can be defined by the location of the canal where the basivertebral nerve and vein enter. This canal is located at the posterior end of the vertebral body. If the peak of the modic lesion is towards the anterior, as seen in the green triangle on the left, then it is further away from the source of the basivertebral nerve and vein. While on the right, if the peak of the lesion is towards the posterior, as seen in the red triangle on the right, then the edema is near the structure where the nerve and vein are largest. In this location, we would hypothesize that the edema is affecting the structural integrity of the bone that is supporting the nerve. Furthermore, this proximity to the source of the vein may change the nature of the microvasculature that forms in response to injury. Based on the mantra that structure is function, one would hypothesize that proximity makes a difference. We next created phantom modic gradients to show the precision with which we can measure shape changes along a continuum. Here are some examples of the shape gradients that we created. They go from shallow lesions on the left to progressively deeper lesions on the right. Focusing our attention to theme 1A, this is how the LCPC transform sees each shape. Based on these frequency plots, multiple indices can be created to track the progression. For simplicity, let's just focus on bins 12 through 20. Starting with bins 12 through 14, on the bottom left, we see that they show a consistent decrease going from left to right. If we sum the values of these bins into one scalar value per shape, then the graph on the right shows a consistent exponential increase of this index. This particular index is useful because it is intuitive, meaning it matches a change in shape that can be visually seen at the top of the screen. The deeper the lesion, the higher the index value. However, the LCPC transform also shows counterintuitive polynomial changes that are hidden to the naked eye. The graph on the left shows the values of bins 15 through 19 for this shape gradient, with the arrow pointing out that the second shape in this series does not follow the trend of the other shapes. Now, when we sum bins 15 through 19 to derive their scalar value for each shape, we see that there is a dip in shape 2, as outlined in red in the graph on the right. Shape 2 represents an inflection point, which indicates some form of an equilibrium state within this gradient. If we had created a finer gradient system, we would see a broader red dip. The polynomial pattern observed in green and red lines on the graph on the right is counterintuitive because we do not see visual evidence of this effect when examining the shape gradient at the top of the screen. These polynomial inflection points are common features when the LCPC transform measures shapes, but are invisible to the naked eye in measures of area and volume. For more drastic examples of inflection points and polynomial patterns of shape changes in a gradient of shapes, please see this use case video on the shape of crescent cells in sickle cell anemia. It can be found on the use cases page of our website. Let's now discuss two potential approaches for systematically grading modic types based on modic shapes. First is the dataset-specific approach, common to image classification models in machine learning. Let's just focus on modic type 1 for now. We would analyze actual MRIs of modic lesions in a particular dataset and then measure the modic shapes. A simple approach would be to calculate quartile thresholds of how the data spreads in modic type 1 patients. We would then compare the clinical outcome features between the 4 quartiles to determine if there might be 4 subgroups of what is called type 1. If we find unknown subgroups, then we would validate this in another dataset of type 1 patients. The second approach is more labor-intensive. It is the universal standard approach that creates a gradient chart meant to generalize to a larger population. We would correlate type 1 modic shapes with sex, age, and other clinical risk factors of pain. This then allows us to create a universal standards chart, similar to the growth charts for children seen in medical clinics and schools. I want to briefly discuss deep learning and the LCPC transform because this is a common question among those who already employ artificial intelligence and machine learning. Deep learning requires the user to define ground truth, while the LCPC transform helps the user to discover new ground truth. Deep learning and the LCPC transform can be used in conjunction to get the best of both worlds. In conclusion, I hope you've been thoroughly convinced that the LCPC transform measures shapes in ways that area and volume cannot. It measures shapes in a way that provides cleaner data than does area and volume, which means machine learning models are less likely to be overfitted. Lastly, the LCPC transform is poised to pave the way for fine-tuning the Modic scale in ways that measures of area and volume cannot. For consulting services and software licensing, please contact us at info@brainscanology.com.